Okay, welcome back to Flipping Physics. What we're going to do today is the calculus way of getting those really cool physics equations. If you recall, we started with an equation that was really x as a function of time is equal to x initial plus v average times t. Okay? So if we use that equation and we start with that equation, then you can have some fun with it and start talking about some calculus. So the other equation was the definition of an acceleration, which was dv dt. So that's the instantaneous acceleration. If you want the instantaneous velocity, it's dx dt. Okay? So from a calculus point of view, here are the equation B, calculus version, equation A, calculus version. Okay? So if you have some fun with this stuff, you can go dt times A equals dx. Sorry, dv. Okay? So if I integrated this and use a definite integral so I don't have to worry about constants, this would be from t initial, which is usually 0, and a t final that we don't even bother writing the t final on it because it's really t final minus t initial, but it's really just t. Okay? The a is constant, so if we use a constant acceleration, we could integrate and pull the acceleration out, and then integrate this from v initial to v final over here, and we got dv. And if we integrate that, we end up with a t equals v final minus v initial. In calculus class, it's evaluating the integral of dv equals just v, and then you plug in v final and v initial, and you subtract. Over here, it's really t final minus 0 times a constant a. But if you notice it, that's just that other form of the equation that I taught you. This written in a different form. So we ended up with equation B when we did the calculus for that thing. Is that kind of cool? Okay. Now, if we let's see, let's just extend this page. I think I can do that. If we extend that page, then if we integrated it again, if we now have v as a function of t equals v initial plus a times t, and we integrated it again, v is rewritten as dx dt. Another way of writing the instantaneous velocity is the first derivative of the displacement. So that equals v initial plus a t. And if I do it again where I integrate with parts, you got dx integrated from x initial here, x final here, equals vi plus a t dt. Integrate that from t initial, which is usually 0, t final over here like that. And if I integrate that, I end up with x final minus x initial, because the integral of dx is x, and then you plug in the top limit and the bottom limit. And then over here like this, v initial dt is v initial times time, and then plus at, and then t squared over 2. Remember that? Where it's the exponent, which is really the 1. You bring it up to the second power and divide by whatever you did. So it's at squared over 2, or just 1/2 at squared. Look familiar? That's equation D. How cool is that? Okay? So you can actually get equation B and equation D right from straight calculus. Let's have some fun again. Let's try it over again. We got dv dt equals a. So therefore, dv equals a dt. But this time, I want to see if I can come up with a way of getting rid of time. Okay? So you want a little sneaky thing here. Watch this. Before we get to this section with the time in it, why don't we multiply top and bottom of this side by dx over dx. You can do that. Multiply the top and bottom by the same thing. You're multiplying by 1. I want you to notice something really cool that happens when you do that. Dx over dt shows up. Well, everybody knows that dx over dt is v. So really I got v dv over dx equals a. Isn't it pretty sneaky, huh? So now v dv equals a dx. Okay, and if I integrate this, v initial is the bottom limit, v final is the top limit, and I integrate this, x initial is the bottom limit, x final is the top limit, and I integrate that, what's the integral of v dv? And the answer is v squared over 2, evaluated from v final to v initial. And over here, I just get a delta x. X final minus x initial. Okay? And if that's true, then over here, this is just v final squared minus v initial squared all over 2 equals a delta x. And if I move the 2 over and move that, I get v final squared equals v initial squared plus 2a delta x. And I don't know if you recognize that, but that's that equation E that I shared with you. And that equation E is the one you use when time isn't given. Okay? Isn't that kind of neat that you can actually use calculus to figure all that stuff out?